Hi, everybody. My name is Josh Devins. Welcome to my talk on modern NLP in the Elastic Stack. I'm a senior principal engineer at Elastic, working on the machine learning team. As the title suggests, today's talk is all about NLP, that is natural language processing, and the effort we're putting into building some exciting new capabilities into the stack. So the talk today is divided into three parts. In the first section, I'll give a very brief overview of NLP and modern NLP, followed by a description of how we're adding NLP into the Elastic Stack, and finally a short demo showing some of our progress. Okay, so let's start with just a brief overview of what NLP is, so everyone is roughly on the same page in terms of concepts. So NLP, or natural language processing, refers to the way in which we can use software to manipulate and understand natural language, as in spoken or written text. And this is a large space of study with roots in both linguistics and computer science. And today's NLP is largely statistical in nature. That is, we try to understand language through counting things effectively. So you contrast this with what was more historically a linguistic approach, which has more to do with human evolution than computers. So a linguistic approach might look at the roots of words and their history as they've evolved versus a statistical approach, which looks at how words are used, how frequently they occur in a body of text, what words are used together or in a particular order, and so on. And NLP has a long history, over 40 years of evolving approaches, along with increased computational power, larger data sets, and these things have sort of changed the landscape over time. And as of about 5 years ago, most NLP was performed using things like rule sets, dictionaries, regular expressions, and some classical machine learning techniques. And in around 2008, there was a breakthrough. Google released BERT, which uses a new type of deep learning, deep neural network architecture called a transformer. And BERT, the model and the approach, was so good that it reached new heights and near human level capabilities on a series of standard NLP benchmarks. And BERT signaled a paradigm shift in NLP. And so as a result, this was the result of a few different approaches and capabilities that all came together. So first of all, data sets are now measured at internet scales. We're not learning from a handful of news articles published maybe a decade ago or two. We've got the entire Wikipedia. We've got hundreds of thousands of books scanned by Google and every web page published on the web. So a continued increase in computation power, decrease in cost, as well as GPUs, so that is graphical processing units. These types of things being sufficiently inexpensive. These have added fuel to the internet scale dataset flame. Machine learning methods have also evolved in the last few years, with deep learning methods becoming some of the most powerful machine learning models ever. So most importantly in this story, BERT cracked the nut of something called transfer learning. So how does BERT and how do the related models with the transformer architecture, what do they do? Well, it all comes down to how these models are trained. So BERT is first trained on internet-sized data sets, but without any human involvement. So more classical NLP models are trained using examples, but these are limited in number, the number of examples that we have, typically because it's a human that needs to label words or sentences in the data set, and then the machine learning algorithm is told to learn based on these examples. So in the case of BERT, the approach is we withhold information and use the withheld information as part of the learning task, meaning we can do this on extremely large data sets without a human involvement. So here we can see an example of the two learning tasks for BERT. In the masked language model, that's the first task that you see, we remove words and try to make BERT predict them. So we have the man went to the blank to buy a blank of milk. We know the correct answer from the sentence is store and gallon. So we can give this as an example of a positive example, saying, yes, these are correct placements for these withheld words. We can also give the model incorrect answers or incorrect examples. And we can do this in an automated fashion by randomly selecting words to place in these placeholders. In the next sentence prediction task, we present BERT with the correct next sentence or a random sentence and try to make BERT predict the correct next sentence. So again, we could see the correct next sentence should be, the man went to the store, he bought a gallon of milk, and not, penguins are flightless. So we can do all of this in a somewhat automated fashion. So no human needs to go in and put these examples in. We can simply select them or withhold them from the data set that we're using for training. From this first round of model training, BERT is able to gain a general language understanding. And so transfer learning allows BERT to a BERT model to be pre-trained for general purpose language understanding. And once it's been pre-trained, just one time, it can then be reused and fine-tuned for more specific tasks. So for example, we could take BERT and use a labeled data set of sentiments associated with movie reviews, as in this example, and learn a fine-tuned model based on this data set. So by pre-training, we bring in a huge amount of general language understanding to this and any subsequent NLP task. So we have the pre-trained model, we have a labeled data set in this case, and we bring these two things together in a specific task, and we get a new model, derivative model, if you will, that is the fine-tuned model. So these fine-tuned models with their general language understanding are the real power behind BERT and transformer models in general. So we're going to go through just a few quick examples to show what is possible with modern NLP. And so you saw the sentiment analysis example in the previous slide. And this is really about performing what would more generally be called a binary classification task. So taking an input, in this case, it's a sentence, and trying to associate one of two labels. So in this case, a positive sentiment, yes, it was a great movie, I really enjoyed it, versus a negative sentiment, yeah, in this case, someone didn't like this movie. Another very common task is something called NER, or named entity recognition. And this fits in the category of concepts called information extraction, where we're trying to build some structure from unstructured text. And this is often not used by itself, but is used in combination with other experiences like search and discovery applications. And so in NER, we're trying to extract, in this case, with this particular model, people, locations, organizations. There's also a category called miscellaneous. And we can see it works pretty well. This is a real model with a real example. It finds my name pretty easily. Berlin as a location, Elastic as an organization, Mountain View in California. Another pretty common task that people have encountered, I'm sure, on their daily basis. Like in my case, I live in Germany, but I translate a lot of things to and from English. So translation is also a downstream or a fine-tuned task that you might want to perform with these models. A couple of tasks related to paragraphs, or what can you do with paragraphs of text. So we have a task called summarization, and this is basically the idea of taking a piece of text, like a paragraph here, this extract from the Amazon rainforest Wikipedia article, and trying to come up with just a concise summarization of the contents of that paragraph. And this can be quite useful in a lot of use cases. Also using, in this case, we're going to use the same example, using a paragraph as input, we can perform a task called question answering. And in question answering, in this case, what we're looking to do is take a natural language question and extract the answer. We call it a span. We extract the answer from the input paragraph. So we can ask a question like, what name is also used to describe the Amazon rainforest in English? The answer is the Amazon jungle, or Amazonia, and you can see the section where it's been extracted from. You can also ask a question where the words used are quite different from what they appear in text. So I can ask, how many countries does the Amazon cover? The answer is 9. But you can see that none of those terms actually appear anywhere in that paragraph, and it's extracting it from this region includes territories belonging to 9 nations. So it understands this general language understanding that I was referring to with the BERT model, and understands that when I'm talking about countries and nations, we're talking about the same thing. Okay, so now that we've seen some of the history and capabilities of modern NLP, what makes us want to bring this into the Elastic Stack? What value can we bring by integrating these technologies into the stack? And how do we make all of this available in the stack? So in the following section, I'll walk through how we plan on integrating these types of models. I put one caveat in front. Please note that this is an early preview of this feature. It will be coming in a future release, but details are subject to change. So let's first have a look at what's the value of NLP directly in the stack. So the first thing that comes to mind is infrastructure and model management. So as a user, you don't have to worry about where and how do I deploy my model? How do I get it into a cluster? How do I get lots of CPUs available for performing inference? So for performing these types of predictions that we want to do. So one of the values is, of course, we take care of this sort of coordination layer and model distribution. We also take care of distributing inference around a cluster. So if you want to make a prediction like a sentiment analysis type of prediction, and you want to do this at large scale, by doing it in the stack, we can take care of distributing these inference calls around a cluster in order to make really good use of the cluster resources. And of course, in the future, in cloud, for example, we can also do things like auto scaling. So if we see that inference load is high, we can scale your cluster up or down as inference load decreases. Performance is the other thing that comes to mind. So by having this in the stack, we can do things like optimizing network hops and costs related to network hops, trying to keep things within the same availability zone, for example, moving data around as little as possible. And in cloud, we can also select and optimize VMs for CPU-based inference, which helps keep costs down. Something related, maybe not applicable for every customer, but data privacy and compliance comes to mind. So by doing all of this in the stack, you can really keep your data within your data center or within your VPC in the cloud in order to ensure that data doesn't leave your secure network for privacy and compliance reasons. So when we think about integrating NLP into the stack, a few initial goals come to mind. One, of course, as you've come to know from Elastic, expect from Elastic, is a good user experience. So this is one of the goals in our mind. It should be easy to upload models. It should be easy to manage those models in the cluster. And we should be able to to provide you with the tooling and visibility to ensure confidence in your deployment. One of the aspects of modern NLP with transformers that's hard to ignore is that many of the models are very large and can be slower to perform inference than previous generations of models using different architectures, different ML technologies. And so in order to provide the best performance, we want to make sure that we can really make use of all of the nodes available in a cluster. Also to provide low cost and good performance, again, we want to make sure that things like CPU inference works very well and very efficiently, as that's a big cost savings. Similarly, we want to make sure that when doing inference at scale across many documents, that we can achieve acceptable levels of throughput. So that is, each individual inference call may not be as fast as possible, but we are then able to handle a large number of concurrent inference requests and process that sort of bulk, if you will, with high performance. So in order to make sure that we could achieve these goals in our first release, we did have to limit ourselves a little bit, and we chose to support, for example, BERT-like models only. That is, models that use the same tokenizer as BERT does. That's an algorithm called WordPiece. So models like BERT, Electra, DistillBERT, these would all be supported. We've also limited support to a small set of specific NLP tasks. And you'll see, you've seen some of those examples above, and you'll see some in the demo as well. And we've done this to make sure that we get the most common tasks right from day one. We're also focusing all of these efforts on inference only. That is the task of taking an already trained model and making a prediction with it. So there's a bunch of excellent libraries out there for training NLP models. So we're leaving that to other tooling for now. So whether you're training your models with libraries like PyTorch NLP, Hugging Face Transformers, Facebook FairSec, you'll be able to import any BERT-like models into the stack and perform inference. Right. So in addition to focusing on inference only, we're also focusing specifically on inference at ingest time. So that is, as documents are being ingested, you can perform inference on them before they are indexed. And in future releases, we are planning on introducing inference on search results, as this is a really important feature for many modern search applications. But really, all of these limitations help us get this feature out to real users as soon as possible. We want to gather feedback, feature requests from all of you so that we can iterate and make sure we're providing all of the capabilities that you need for your specific use cases. All right, so to make all of this possible, of course, we need some kind of machine learning library with which to perform inference. And for that, after much research and prototyping, we chose PyTorch. And PyTorch is one of the most popular modern machine learning libraries with a very large community of active users. And it's one of the libraries that supports deep neural networks like the transformer architecture, which BERT uses. PyTorch also has very broad adoption across both research and industry, which is important as new models, new approaches come out of research or come out of industry. We see that PyTorch is one of the libraries that is used most frequently. It's also well supported and actively developed and maintained by Facebook. They're the official maintainers. And one of the most important things for us was making sure that the APIs were stable and functionality was stable. So we wanted to be certain or more confident that, for example, between a version upgrade of PyTorch, that a model trained on a previous version would work well on newer versions of PyTorch. And we found that in PyTorch. Now, to make all of this work, the astute among you may be wondering, well, does that mean there will be a Python interpreter in the stack? And the answer is no. We will be using the native library, which backs PyTorch, and that's called libtorch. To make all of that work, and in order to use libtorch, we will only be supporting PyTorch models that have been exported or saved as what's called a torch script representation. And this is the representation of a model that libtorch needs, and what will allow us to avoid running a Python interpreter in the stack. Okay, so how do we get all this to work in the stack? And as a data scientist or user of the stack, what might your workflow look like? The first thing we need to do is get our models uploaded into a cluster. So to do this, we'll be providing a couple of different mechanisms. As always, there will be REST APIs that could be used from any client, but we also want to make sure that there are very simple tools that help with this process. So in our ELAND library, which is our Python data science library for the stack, we'll be exposing some very simple methods and scripts that allow you to upload models from your local disk or to pull models down from, for example, the Hugging Face Model Hub, which is one of the most popular ways to share trained models. So for either of these approaches, there will be tooling to help convert PyTorch models into their torch script representations as well, or you can do it on your own. We'll also provide some tooling to do things like simple model optimizations like quantization, which is a method to improve the performance of a model. And finally, of course, to upload models into a cluster. So once models are uploaded into the cluster, you'll be able to then allocate these models to specific machine learning nodes in your cluster or in cloud. And this process makes them ready for inference by loading the models into memory and starting the native libtorch process. Once model allocation is complete, we're ready for inference. So as mentioned previously, we're focusing our efforts on inference at ingest time only. So there will be an ingest processor for inference, and you can set up any kind of ingest processing pipelines to pre-process, post-process documents before or after inference. So in this example, we have a sentiment analysis task, again, where we take text from a document field as input and return either the positive or negative class label that was predicted for that input, and simply add that prediction to an output field in the document. And it's simple as that. Okay, so now we've had a short tour of modern NLP, talked through how PyTorch will be used in the stack. Let's have a look at a quick demo which shows some of these pieces in action. Before we jump to this demo, I will just repeat, this is a pre-release demo. So things like APIs, naming conventions, and so on may look different in the final release. So here's a Kibana instance. I've already uploaded a model. It's an NER model that I've pulled down from Hugging Face Model Hub. And again, using our tooling, made this available, uploaded it into the cluster. And here you can see this is the model that I've chosen. It's one of the most popular BERT NER models. So we're going to perform NER tasks, so extracting entities. So here you can see just a simple preview of what the model looks like. All right, so now that we have a model available, let's just have a quick test to make sure that it works. We're going to use this simple sentence here. Hello, my name is Josh and I live in Berlin. And let's see what it does. And here you can see that I'm just referencing the NER model with its ID and calling inference, and hopefully, yeah, okay, it's extracted my name and my location. Perfect. So the next thing we're going to try and do is create a ingest pipeline. And it consists of two processors. The first is the inference processor, again, just referring directly to the model by ID. And this is the same inference processor that you would see with any other ML models in the stack. And so we're going to take the output of NER and we're going to put it in the subfield _ML.NER. And then the second processor in our pipeline is going to take these results, as you can see in this example here, these entities, and it's just going to extract the word and the label, and it's going to restructure it into a tag. And we'll see what this looks like after it's created. So good, that worked. Now we're going to ingest some documents and run all of these documents through the NER pipeline that we just created. And these are all just examples here, but you can see, yeah, we reference Elastic, which should be an entity. We reference some names. So let's index all of these, and then hopefully we can see how it all works. So this is now run through the pipeline with it's performed inference, and it's stored all of these documents. So let's just have a look at one of these documents and make sure it looks as we would expect. So here's the same example that we looked at before with the same results. And we've left the results in here. Normally the sort of raw results, the _ML, you might want to remove. So this section, and what you're left with is basically tags per entity type. So in this case, it's stored these as keyword fields. And so we have keyword Josh and keyword Berlin for the person and location of this document, which looks correct. Okay, so let's do something a little bit more interesting. So here we're going to do a search for organization Elastic, and we should end up with 3 documents. Let's see what happens. All right, this looks correct. So we have I work for Elastic. This is an organization. Elastic has headquarters. This is an organization. And this is a good example here. It understands here that it's been tokenized properly. That understands that Elastics with apostrophe is just extracted the organization entity from this this word. So that looks all good. It's not super interesting. So let's try something a little bit more interesting. And what we're going to do is search for the location Mountain View. And this appears only in one document. However, if you were to have done this search with not just a terms query on the location entity, if you were to have used a match query on the full text, you can see that there is another document that would have matched here with the phrase Mountain View. But because we're searching on the keyword field with a terms query on the entity that's been extracted, it only finds the one correct document here with Mountain View. So that shows one of the use cases where you might want to search only on entities. Hopefully all of this demo gives you a little bit of a sense of what's coming, how it can be used, and gets you excited about using the feature. Thank you for watching. Looking forward to getting this feature out there in front of you, in your hands, and getting lots of great feedback from you. So thanks again.